Great, thank you, Leon. Hi, welcome everybody. Let me see that I have the chat ready in case there are questions. Great. All right, so my name is Jill and I'm a postdoc in the lab of the brain simulation section from Pietrarita, and today will be everything about graph theory. Maybe graph theory to you sounds very much like an area of mathematics, which it is. It will be mostly about network neuroscience and how we can bring graph theory actually into the clinic. And for that, I've prepared kind of a dive from no previous knowledge until in 90 minutes, you hopefully get some nice results, statistical differences between patients and controls with MATLAB. So for that, please make sure you have your MATLAB ready in case you want to follow along. If not, it's also fine. Network science can be done in any other programming language as well. So if you have no preference for MATLAB, you can do the same things in Python or however you wish. All right, so if there are any questions, just put them in the chat. I see the chat here, so I will then read them out loud such that when people later watch it, right, they can see it. And I hope that we will have some interaction over the chat as well. If we dive into networks, then we can see a bit some simple networks, and that I will have some nice questions for you. Let's see how that works and how the interaction is going. I'm very excited to present a lot of network and graph theory stuff to you, because that's actually what I've been doing for the last 8 years. I started studying mathematics and graph theory, and then I ended up doing clinical applications of network neuroscience with the virtual brain. So this is how it can go from the theory towards the real application then. All right, let's get started. So graph theory. For everything we need for graph theory are dots and lines. So let's start very basic and take you all on board with me. We need some dots, we need some lines, and in graph theory, that's the area of mathematics where this is all theoretically dealt with, it's called vertices and edges. One vertex, multiple vertices and edges. So together, once we have this, we can build a graph. So maybe graph is for you a confusing word. So today a graph will be exactly this small combination of edges and vertices. That's quite nice, and people seem to use edges also a lot, and vertices are not so well known. So I wanted to make this nomenclature clear. A short disclaimer, I'm of course biased by all my previous mentors and by all the network neuroscience that I've been doing. And this area of graph theory and network science is so broad that you will see, once you read through papers, so many vocabulary things that you might seem new or innovative or something, and then often you realize that, okay, they just called it differently. So let's set the vocabulary for today. This is a graph with vertices and edges. And now let's look into when was graph theory actually born. That's the obligatory thing you have to do once you start with graph theory. You have to think about the city Königsberg and the famous mathematician called Euler in 1736. He lived in the city Königsberg. The city Königsberg had actually 7 bridges. So this is the river, right? You have an island here, and you have all the bridges here over the water. And then Euler was walking in that city, and he was asking himself, can I actually take a certain walk through my city, crossing all these 7 bridges, but never crossing the same bridge twice? So that's reasonable, right? You want to take a walk in the evening and you don't want to come anywhere twice, but you still want to see all the beautiful bridges. So once Euler asked himself that, he actually came up, which is the first, as we know, graph, where he gave a dot to all these little places, A, B, C, and D, where he wanted to go. And then for every bridge, there was an edge. So this was how he represented the first graph, and graph theory was born. And then the question would now be, can we do that? So if you ask yourself, just see if you can find some walk between all of these 4 dots that crosses all of these bridges, but no bridge twice. And you can try for a long time because there is none. And the theorem that Euler actually then proved was what is called an Euler walk. So exactly the walk with all these different assumptions is only possible if we have either no or 2 nodes with odd degree. If we have no nodes with odd degree, all nodes degree is here actually just the number of bridges connected. So I need to say that short. Degree is the number of links attached to a dot. So here, when you have 0 ones, you just enter a node and exit a node. And do that all the time. Or if you have 2, you just start and end in that vertex. And you would have your Euler walk. So that's how it all started. And then a lot of effort was actually also put into the traveling salesman problem, which is kind of a follow-up question of this one, where there's a traveling salesman and he wants to visit all those cities and he wants to have the shortest paths and so on. So these things also should be well known, but if not, feel free to read up on it. And now let's go from graph theory one step further to network science. So how does that go? We again have dots, we again have lines. And now once we add an application, so we have a certain application in mind, then actually it's called from then on network science. So once we apply graph theory, we call it network science. And then also these vertices and edges are officially no longer called vertices and edges because there we are in the theoretical world, but now called nodes and links. And that's what you often will see when you read through network science papers. And then we have our first network. So this application here is a brain network. Hopefully it's recognizable. All right, and now let's look at different kinds of networks. So we have, for example, these nice small 3 networks, which have all certain names coming from graph theory. So this would be a tree. For example, you can think of your family tree or something. It's always going down and never going back up, and no crossovers or anything. So that would be what we call a tree. Here, this is, for example, a ring. And this is what we call complete graph, because everything is connected to everything else. So all of these nodes are connected to all of the other nodes. And that's a complete graph, or how also it's like to be called in graph theory as clique. Makes sense, right? Like a clique of friends. And now let's ask ourselves, how many links are in a tree? And for that, I want to introduce the number of nodes, which we will say is n, and the number of links, which we will say is L. So can you think of a general expression that describes the number of links in that tree? So in this case, so you might send an answer over the chat anytime if you can already figure it out. So how many links are in that tree? So we have a tree of 1, 2, 3, 4, 5, 6, 7, 8 nodes. How many links? And can we find a general expression? So for the first one, we'll make it easy. This is what I was looking for. The number of links here is n minus 1. Always. For any tree, which is defined as something that has no crossovers, no triangles or anything, it just goes down, 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 children, again, children, again, children. It's actually the number of links is always 1 less than the number of nodes. All right, so for a ring, any idea how many links we have expressed by the number of nodes? Nice. So it's true. The number of links, thanks for that, is exactly the same as the number of nodes. And that's true for all rings, whenever you have a ring. So here in the case, we have 1, 2, 3, 4, 5 nodes, and we have 5 links. So now this is the most difficult one. For the complete graph, when we have every node n is connected to every link, is connected to every other node n, how would we make a general expression for the number of links here? How can you calculate how many links are in this graph? So in this example, you can already send it over the chat. Ah, I see some nice answers here. Great. Yeah, it's not so easy to write over the chat, that one, right? You can, yeah. So I wrote it like this, but there are multiple ways you can write it. I see already an n squared. That could be an n squared here. Yes, and also this one. So it's actually the combination of out of these 5 nodes of all pairs that are actually coupled together. You could call it like n/2 or write it down into this expression. All right, so we have some nice general rules how links and nodes are connected in these nice little cute networks, but we want to later on deal with the brain, right? So the brain is no tree, I can already tell you that. The brain is no ring, and the brain is no complete graph. So let's later learn a bit how the brain then looks, but these are quite simple, small networks. So for a network, we like to look at these beautiful visualizations, of course, because they also help us to make it understand. Yes, and choose to, yeah, good one, exactly right. So they help us understand a network visually and see where maybe there is a node that has a lot of links or where are isolated ones in the corners. But how we calculate most of the things in network science is actually not through just looking at this, but through a matrix. So this is the adjacency matrix, which is most often denoted by A, capital A. So adjacency just meaning adjacent links, right, are marked in there. So we have here a network, small one, of 5 nodes and actually 5 links. So what we always do is we write in the column and rows the different labels for, you can think of some brain regions here or something, but in this case, just 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then we mark their connectivity in this matrix. So I already put zeros on the diagonal. Why did I do that? Because that's the connectivity between node 1 to node 1, and there's actually no self loop or something. So sometimes you will see in some network self loops that are connections between you and yourself. But in our case here, we have none of these loops. So we put zeros on the diagonal. So now I will make it very simple. For the first row, we will think of what we should write here for this particular graph. So we have always from node 1 to node 1, no connection. From node 1 to node 2, we will put that in this field here. Node 1 to node 2, they're actually connected. So once something is connected, it no longer gets a 0, but it gets a 1 here. Is node 1 connected to node 3, node 4, or node 5? Actually not. So this is how the first row looks like, 0, 1, 0, 0, 0. So now I would love to see in the chat what you think should be in the second row. Also just from left to right, a combination of zeros and ones. Let's fill up this adjacency matrix. So I'm looking for the connections of node 2. You have to ask yourself, is node 2 connected to node 1? If so, put a 1. If not, put a 0. Yes, I already see some coming up. Any? Yeah, nice. All right, so let's reveal it. 1, 0, 1, 1, 0 is correct. Great. All right, so now let's make the next row. Not so hard, right? Let's fill up this adjacency matrix and see the connections of node 3. Is node 3 connected to node 1? No. And so on and so on. So again, 5 numbers of ones and zeros, please, in the chat. Now wait a second so that you can follow. Great, I see already some. And yes, they're all so far similar. So yes, it's correct. 0, 1, 0, 1, 0. Why? Because 3 is connected to node 1, to node 2, sorry, and node 4. So we need to put a 1 there and there. Great. Somebody dove ahead and made it all finish up. So let's see if that's correct. Node 4 is connected to 3 other ones. So we should have 3 ones in there and 2 zeros. Yes, and let's see, what do you think of row 4? All right. Ha! I like that answer as well. So somebody suggested we just fill in half of the matrix and then transpose it, because then it's symmetric. So we don't even have half yet. So let's make it row 4, and then everything is indeed symmetric. So row 4 is 0, 1, 1, 0, 1. Great. That was correct by everybody. And now we have already the upper triangular of that matrix here, as you can see. And indeed, we have a symmetric network. So meaning that all the nodes, when 1 is connected to 2, 2 is also connected to 1, right? So we see a pattern here. That's what we call a symmetric network. And then also the matrix is symmetric. You can just mirror the upper triangle towards the lower triangle. It's exactly the same. So the 5th row, we could just take the 5th column and lie it down. So this is our first adjacency matrix. So excited. Okay, we filled it up. We understood how an adjacency matrix relates to a nice visualization of networks. But now there are different kinds of networks. And what we just had was actually a binary network. Binary in the sense that you have just 2 options. Either 2 nodes are connected or not. And we call it a binary network. But you also have weighted networks. So that's what we often have in the brain. We don't just have a connection or none, but we have a certain quantity of connections, maybe a number of streamlines. We have sometimes many number of streamlines giving us a high value, and sometimes lower number of streamlines. You can think of distances in a city where you have maybe higher or lower values for longer or shorter streets, or how fast you can go through that street also. So you can think of different ways here, but what it's called is either binary, when you have zeros and ones, or weighted, when you have any other values on the links. All right, we understood that already, great. So in a directed and undirected, so what we just learned of symmetry is actually what we often call just an undirected network. So a connection is always going both ways. For example, you are friends with somebody, and I would put a link for friendship. Then most likely, let's hope for that case, that the friendship is actually undirected, meaning that it's going both ways. And then you have, yeah, bidirectional link, which would be here in the case, for example, between 2 and 3. But here, 1, if we say these are friends and people, then 1 would be kind of stalking number 2, right? So there would be no friendship from 2 to 1. But you can see it also as a flow. There could be water flowing from here to that city, and then to that city, and then here. And actually 5 would never receive and only give here some water towards the others. All right, so different applications you can think of, but what I wanted to say is that this is a directed network that we see, which is always denoted by arrows. And once you have only lines, we're assuming bidirectionality. All right, so we already learned about different kinds of networks, but now where it gets, I think, most exciting, also for brain networks, is the network metrics. What are metrics in this case? It's just measurements. So we want to measure this network. We want to actually come up with something and say, this network has this specific properties, because we want to compare networks. All right, so the first network property that this network we already know, this adjacency matrix we already know, is degree. I already said what it is, so it's a kind of strange name just for the number of neighbors. So, for example, node 1 has a degree of 1, right? That's easy. So please tell me in the chat, node 4, what's the degree of node 4? Just very quickly in the chat, please. Yes, great. Indeed, node 4 has the degree 3 because it has 3 neighbors, 1, 2, 3. So node 5, also 1, very easy. And now I will show you how we can either find out the degree just by looking at this nice visualization, but we can also find out the degree by looking at this matrix. So it's just 2 representations of the same network. So if I look for node 2, for example, I see here 3 connections, so a degree of 3. If I look into the matrix, I can also see that in the row and also in the column for node 2, since it's symmetric, we can either take columns or rows, and we see 3 ones. So that's actually meaning that we can also take just the sum that will be important for our MATLAB exercise later. We can just take the sum of the rows and the columns to find out the degree from a matrix, because sometimes it's so big, right? You cannot even see, think of millions of neurons. And then you have to do it just with the matrix and not so much with this nice visualization anymore. All right, thanks for interacting a bit. So now let's look at a different measure, which is also often, you don't only want to know the degree of a certain node, but you often want to know, if you think of friendships, for example, yes, that person has a lot of friends, but are the friends also friends with each other? That can be very important. So here we see a typical click or complete graph, as we have talked about before. And this is actually what we call a highly clustered network. So cluster is really, in a sense, what you would expect a cluster. Something clustered together, densely connected. So the clustering coefficient, what we call it, is calculated by the number of links that exist between my neighbors divided by the number of links that could possibly maximally exist between my neighbors. So why would that be important? Because this ratio is actually giving us something like, okay, am I part of rather a clique of friends, or am I maybe the connector between different isolated people? Who knows? So to find that out, you can draw your own friendship network as well. It's actually quite nice to do sometimes, and find out what's the clustering there. So the clustering coefficient of a clique, so I'm the blue node now, I have 3 friends. All the 3 friends are also friends with each other. So we have the number of existing links between my neighbors, 1, 2, 3. And what's the number of possible links between my neighbors? That's the maximum number, so it's 3. So my clustering coefficient is 1. Now again, what's the clustering coefficient of this blue node? We can see here that he has, again, 3 friends, but now the red links are missing. So there's only 1 link among his friends. So that gives us 1 existing link divided by 3 possible links. So the clustering coefficient of the blue node is 1/3. And then we have here 3 rather isolated nodes. They're just friends with the blue one and not among each other. They don't know each other, sometimes quite nice, right? If you tell somebody something and they actually don't talk. But okay, let's not get carried away. There is a clustering coefficient of 0 because there are 0 links between my friends. So I don't even have to divide it by anything. The convention is that it's just 0. All right, so clustering is also actually the same as, this is a local clustering coefficient, but there's also something like a global one, looking not only at a single node, but the whole network. And the only thing that's actually counting then is the number of triangles. As you already see, a triangle is something highly clustered. So actually you could just also count the number of triangles in the larger network. All right, the next measure I want to introduce to you is the measure of modules or community. Again, thinking of a friendship network, this could be all of your friends, and this could be your colleagues that are densely connected, one community. This could be your tennis club. This could be your high school, who knows? Maybe there are some overlaps. And so you would have like different communities. And we already intuitively know what a community is, but network science came up with this measure called modularity, which is just calculated by the number of links that are existing within such a module. So quite a lot, right? And you just look at how high is this number compared to the number of links within a module predicted at random. So if I would just randomly put those links in this network, would it look the same? So this is how you can just calculate modularity. Having a high modularity then means that there are lots of links compared to what we expect at random. So it's a very densely connected community in your network. All right, so then there's something like a walk and a path, and I think we have to skip that a bit, but okay, let's shortly do it. So a walk is nothing else than what you would think of. It's a walk through the network, and just a succession of different links. When I want to walk from node I to node J, I just traverse different number of links, and that's a walk. So any walk through a network. And the difference now between walk and path is that when I have a walk, I can take the same link again and again and again. But in a path, I want to take a walk in which all nodes are different. So it also sounds kind of like a walk. You just walk around, you can cross the same bridge again, blah, blah, blah. And a path, you would be more straight, right? You would just not walk and visit any node twice. So that's also, yeah, an often difference that we have to care about in network science. And actually the beauty is we have seen this adjacency matrix A, that once you want to find out what's actually the number of walks between two different nodes through the whole network, you would just have to take the adjacency matrix and multiply it by itself number of times. So if you want to know the number of k-hop walks, so what's a hop? A hop is just what it says, a hop from one node to another node, so just one link. So if I want to know how many two-hop walks exist between me and another person in the network, then all I would have to do is I take my adjacency matrix, fill it up, and then I just take it to the power of 2. And what comes out? The entry of ij in the matrix, where I is always first rows and then columns. In German, it's quite nice. Zeilen zuerst, Spalten später. That's for all the Germans out there, if there are any. There is kind of a nice bridge how to remember that. All right, so we can work with the adjacency matrix or look at the nice visualization, however you prefer. But once the network gets bigger, be prepared to look at some matrices. All right, so this there's a network metric called hop count, or maybe you know it better at the shortest path length. So here we see already there's the nomenclature in network science, which is such a broad field, can be quite different. So I define here the hop count as the number of links in the shortest path between I and J. So now we no longer take a walk, but we want to take a path, and not any path. We want to identify the shortest path between two different nodes. So in this case, we have here the nodes D and E. So if you want to identify now the hop count or the shortest path length between D and E, please write in the chat how many links you think are in the shortest path between D and E in this network. Yes, I already got the right answers. Yes, 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 4 is correct. All right, why is it 4? Because we want to minimize that number. And we actually, if we want to go it, we have to go through A here. 1, 2, 3, 4. Taking any other path would actually make our path longer. So this is the shortest path, or hop count between D and E is actually 4, correct. So now there's something called the diameter of the graph G, which is just the largest hop count in G. So it's the longest, shortest path between any two nodes. So what's the diameter for this particular network? In the chat, please. We want to see now the number of links in the shortest path between any pair and then the maximum of that. So look at this network. Do you find? I like the answer infinity. Infinity would be if indeed the network is not connected and we can actually not get from any node to any other node. Then it's correct that the diameter would be infinity. But here the network is connected. We don't have any isolated nodes, so no node with no friends. So we can get from any node to any node. So what you would have to do is go from this one to this one, from this one to this one, to this one, this one, this one, this one, and so on, and try it all out in your head. Okay, I see a lot of answers. Yes, so, okay. We would have to try it out. Let's look for a very long path, but let's take the shortest path between them. So between D and E, we've seen is 4. Could there be any other node pair that is quite far away from each other? Maybe here, 1, 2, so that's 1 link, 2, 3, 4. Still in 4 steps, I'm there. Maybe from here, 1, 2, 3, 4. Still in 4 steps, I reached that one. And so on. So you can do it in any one. So it actually is 4, I would say. But we can easily also do that over the adjacency matrix, actually. Because I don't find the path of 5, or I don't find a shortest path, a shortest path of 5, or a shortest path of 10. No, so here's somebody was a comment, if a closed loop exists, isn't the largest number infinity then in that sense? So there is a closed loop, yes. This network is actually connected, everything is closed, and then it's not infinity. If the network is completely connected, you always have a way to get from A to B. So that way you can always count the length of that way, and then you would have a shortest path between them. But if we would have a node here, very isolated, he cannot connect to anybody. And then by definition, his distance to any other node is infinity. All right, and then there's something called the average hop count. So the diameter was the maximum length of the shortest path. Then we can have the average length of shortest path between any two nodes, which just is the efficiency of transport. Or in the brain, maybe the efficiency of communication, or the efficiency of our white matter network, which is an important measure and often gives us a nice indication of how well that network is actually connected. And it's the same, maybe you have heard of characteristic path length, so that's also often called characteristic path length, depending on which area of network science you're into. All right, so with that, let's start with network science. I've already talked a bit about networks, right? So now let's look at some beautiful networks. In the background here, you see the well-talked network these days that everybody talks about, air transportation. This is actually the air transportation network, which allows the spread of quite a lot of viruses, right? And now let's look at the average hop count actually in the world of humans. So we imagine every person is a node and there is a link when two persons know each other. Then Milgram and colleagues have done experiments back in the day, so already 50 years ago. They sent some letters. You got a letter sent by Milgram and colleagues, and they said, this letter should reach the President of the United States. If you don't know the President of the United States, just send it to somebody you think is closer than you to the President and is more likely to send it to him. So what came out of this nice experiments was the famous 6 degrees of separation. So the whole population, and many people have repeated these experiments afterwards, still this theorem is true. that we have 6 degrees of separation in the world, meaning that you are just 1, 2, 3, 4, 5, 6 handshakes away from the president, for example. And often this is has been found in many other networks, not only social networks. And it's called the small world property. So aren't we living in a very small world? Every other person is reachable from every other person just by 6. So 5 intermediary people in between you and any other person in the world. But then, of course, we don't only have the real world, but we have the digital world. And Facebook has done and published some of his research on that, that the degree of separation on Facebook is actually not 6 as it is in the real world, but digitally we seem to be more connected. In 2008, it was 5.28 hops in between you and any other person. 2011, 4.74, and last time they published on this, I checked, was 2016. And there, everybody from everybody else on Facebook was just 3.57 steps away. So just 3.5 persons in between you and anybody else on Facebook. That's very well connected. And now don't, kid yourself how a pandemic can spread. Isn't the efficiency the inverse of the characteristic path links? Yes, that's true, Leon. That's just another name of how we can call this measure of how well connected the network is. You can either calculate the characteristic path length, like 4 or something, or there's another measure called efficiency or global efficiency, where you just take the inverse, 1 over 4 or 5. And then it's called global efficiency. So there are lots of words for basically the same property of a network. How well is it reachable from any point to any other point? Yeah, great question. All right, so network science is more than just a brain. I'm giving here 2 examples of where this area of network science has also been applied. Upper right corner, there's a nice review on banking networks. So you see different banks, and when they actually gave money in between each other, one bank is borrowing money from the other, they have a link here. And with these kind of networks, they, for example, explain the financial crisis, and the Lehman Brothers crisis. And here on the lower left, you can see a smart grid, for example. When I was doing my PhD in a group with network science, different people and many of my colleagues worked on smart grids. So that's actually about building a network between homes and exchanging energy in the right way and dividing it. So that's also a really huge area of network science. And now in the chat, I would just love to see more examples that you have maybe already seen, where you can think of where there are networks in research in our world out there, where you could imagine that network science could be a nice addition or something. Can you think of any area of network science? Then please put it in the chat. We have smart grids, we have financial networks. What else is there? We have the brain, yes, I can say that, brain networks. But what else? Everywhere is a good answer, indeed. Yeah. But any other objects in particular that you could think of that you see as a network, that you've seen today as a network? Political preferences, yes, I like that one. Ecology network, yes, there's a lot going on ecology networks between different species, the connections, one species eating the other species and so on. Yeah. You probably know all kinds of social networks, like Twitter, Facebook, right? Your own friendship networks. If it's your own, it's often called ego network. And so it's actually quite fun on a network science conference. You see all those researchers from all those different areas. There are climate networks. Public transport, yes, oh, that's a great one. There's so much going on about train networks and optimizing trains, and it's quite difficult because once a train is delayed, right, you think of like different how that would spread through the networks, this delay, and how you can still stop it or minimize the delay. It's quite a cool, yes, infection chains. Yeah. So that would be social networks, and there would be a virus spreading on top of it, and an infection chain is also nothing else than a network. ANN, artificial neural networks, yeah. Huh. Too late, yeah. Yes, totally correct. Any machine learning algorithm also feeds on network. And what's behind there, as you've seen last week, is just also a beautiful network. So, okay, we can finish this up. Because I do network science for such a long time, right? I see networks everywhere. And maybe you too, and probably tomorrow you will as well. Okay, and here we have an overview, a very recent one, over the last 20 years of network science, because it's quite a new area of science in that sense. And you can see that these are the top 10 areas where network science papers were published in. You can see that with neuroscience and neurology here, the brown line, we're doing quite well. Yeah, of course, there's more physics and engineering going on, but we are doing quite well, and we are, not rising in 2019, but hopefully now. So many different areas where there's network science going on. So don't only think you have network neuroscience, but you have so much more and so many other areas where we can also nicely learn from. But now let's dive into some brain networks, network neuroscience, or connectomics. It's all the same, just different words for it. All right, here we go. And our brain network, as you most probably have already seen, is beautiful. We can just divide the brain into regions and then figure out the links in between those regions, having the regions as nodes and these fiber tracts as links. And then what we would really need to use this is the parcellation. So that's the division of our brain just into different regions. Those regions become the nodes and the fiber tracts become actually the links in between. And then we can also take this network completely outside of the brain and analyze it on this very abstract network level. So let's look at some examples. So here, for example, we've looked at the network science perspective on Alzheimer's disease. So in Alzheimer's disease, people have been analyzing these brain networks for a long time. And actually, this is what I thought is a good summary of what's going on in Alzheimer's disease. If you think of this network as our brain network of an Alzheimer's disease patient, the internet, yes, correct, another network, the internet, an Alzheimer's disease patient, and then the red links would be the links that are weakened in an Alzheimer's disease patient. Why? Because what's most important and most often confirmed in Alzheimer's disease is that the nodes with a high degree, so for example, node A has a high degree, it's called hub, then these nodes are very vulnerable to the disease. So these nodes will be attacked by the disease of AD, and their links will be preferentially weakened. And at the same time, that's not all going on, but also the clustering, which we have seen is just characterized by these triangles, will be weakened in Alzheimer's disease. So for example, this red link will disappear. Before it connected B and C, and now it's disappearing, giving A, which is a hub, very important, a lower clustering coefficient. And then here we have these links, for example, here, like link E, it's actually weakened in Alzheimer's disease because it's often is the case that actually we have a lower efficiency here, meaning a longer shortest path. And this link would actually be very important. Once we delete this one, we go from a diameter of 4 to a diameter of 5. Maybe even 6. 1, 2, 3, 4, 5. 6. All right. That's something for figuring out for tonight. Okay, so that's the perspective of what's happening from AD in this abstract network level. All right, so let's dive into what is network-based statistics, because we want to often do some statistics on a network, but we have so many links that we are often overwhelmed when we want to compare differences between controls and patients. So let's think of this as a weighted network of, we have the weighted network of a bunch of controls and a bunch of patients, which we will have in a second actually, really in MATLAB. And then we want to compare them. When we compare now every link with each other, we would actually have so many different links that once we do like a t-test on them, compare what's the value of this link between controls and patients, we would get a nice p-value for it, but we would have to correct for multiple comparisons for so many multiple comparisons, because the network often has so many links, and especially in the brain, we have thousands of links. In between only, for example, 80 nodes, you might have 3,000 links. So once you correct for multiple comparisons, you actually have that no link is significantly different anymore, because you will never reach that very low p-value threshold. And for that, network-based statistics is born. But we have a question: why is the hub more vulnerable to AD? Shouldn't it be less vulnerable as it's less isolated? So that's exactly the problem of AD. They found that these hubs are attacked by the disease, and their links are weakened more than any other links. So making the network of AD patients then much less efficient to reach different states. So you can think of it reaching a memory back in the head of your brain network makes it then much more difficult, because it's not so well connected anymore. And it's especially attacking those hubs, which are so very important for the communication of the different brain regions. So yeah, unfortunately, these are the hubs, and they are more vulnerable. But yeah, it's multiple papers published on it. It's just what we unfortunately see, that the disease attacks these very central places. All right, so once we do a t-test now on all of these links, we would get different t-values, which t-values are actually, you can convert t-values to p-values very easily, but it's the value of t-statistics. Once we do it for every link now, a certain t-value, so we've done a t-test on every link, we would have to correct for these multiple comparisons. And then nothing would stay significantly different. So there's a trick. We now set a certain threshold on this t-value, and we keep only the links that have not a significant one, but a very high, like a very low one, which could reach it. So a very low p-value, or the inverse is actually true for t, so a very high t-value. So they have a very high t-statistic. So they could be the ones being significantly different if we do a little trick here. And the trick is now to take a step away and see where are the links that are nearly statistically significantly different, and find the largest topological cluster of these links. So here in this case, we have a cluster of many links and nodes, and these are just smaller ones. And the size of this cluster is actually 6. So the number of links in this cluster is 6. And then the only thing we ask ourselves is, hey, it seems like we have a cluster there of very interesting links. So is this connected component actually larger than expected by chance? And this chance, we will just try out shuffling controls and patients, mixing them, making 2 new groups, doing the same thing, and seeing if still we have this same size, the same pattern of very interesting links. And then we can actually say, with this network-based statistics, we can find out these clusters of different links between patients and controls, with this little trick of not looking at the links directly, but taking a step further away and looking at the patterns of these low p-values. All right, let's dive into, oh, sorry, forgot the question. Yes, so Leon knows all about these theories about the hubs and Alzheimer's disease, of course. Thank you, Leon. And was that modeled on TBB as well? Yeah, so that's very important. You can chat about it. And Leon will send you the right links, hopefully. Otherwise, after the lecture, I can have a look. So let's go away from Alzheimer's disease and have a short look on this disease, amyotrophic lateral sclerosis. It's a horrible disease. Maybe you know that Stephen Hawking had it, or maybe you know this ice bucket challenge, where you can see here my former boss, Leonard van den Berg, the head of the ALS Center in Utrecht. And it's a fatal disease where the median survival time after symptom onset is 3 years. So 50% of patients die within the next 3 years, and another 50% live and can also live much longer. And what is this disease about? It's the motor neurons that get degenerated, and it's spreading through the brain and can also cause cognitive deficits. So I worked a lot on this disease. It's quite rare and there's no cure yet. And I did this network-based statistics on this disease. So I took the brain network of ALS patients, compared them with controls, which we will do as well in a second. And then I looked at these largest connected components of low p-values. And these were always around the motor cortex. And actually what I found was that if I look at the patients over time, these components that were different between ALS patients and controls are growing. So the degeneration of the network is spreading and actually growing inside the brain network. So this is what we found over time when we compared patients at their first MRI scan versus their fourth one, which is approximately 2 years later. So we have growing impaired connected components. And now this is not all that we want to do, right? We want to not only observe with network science, but we want to take it, build a model and predict what we think is happening. And then compare this prediction with the empirical impairment. So I developed a computer model that can simulate how this disease, ALS, spreads through the brain. And how does this model look like? It's actually quite easy to understand. It's a random walker, we call it. He is walking on the brain network of a patient on the white matter fiber tracks, and more precisely on the weight here on this link is the number of streamlines. And otherwise, he's just biased. He's always choosing a link and can walk anywhere through that brain network. And he will multiply itself and so on. So it's a bit more complicated, but this model is a random walker walking on the structural network, and it models this impairment of growing impairment from the motor cortex to the other regions. So when we do this, we can count how many times was a random walker actually present in that region or not. These little people would just walk, right? And then we can see that the random walker was present quite often in the motor cortex, where it actually started, but it also visited nearly all other regions because the brain is very well connected. And the impairment seems to spread. So then we looked at these aggregation levels based on the first scan, and we looked what's actually happening on the fourth scan, and we found a high correlation. So we could predict with our little cute model of the random walker what would happen in a brain 2 years later of an ALS patient, just by using network science and this abstraction level. So this is one example where I wanted to show you how we can bring network science to the clinic, where it can actually help us, in this case, to predict which other regions will be affected at a later time point. This was done for the average brain, but I also did it for individuals, also worked there for individual prediction. And we had a correspondence actually with the Brettschneider stages, which were also already shown before in these lectures, that was found that these random walker levels, so the regions that the random walker visited, had a correlation with the Brettschneider stages. In the higher stages of Brettschneider, the earlier ones, the random walker was more often. All right, so it had some relation even with post-mortem observations. And then it was not all, and I wanted to show you now how we build this into a machine learning algorithm, because last week just you learned everything about machine learning. So there was a previous study by my PhD student, Hannelore, where she already tried to predict the survival class of an ALS patient based on his or her data. And the data was made out of different clinical characteristics that went into this deep learning network. Also the structural connectivity, this matrix we now know all about, and also the brain morphology here as the cortical thickness. All of these things went into the model, and out came whether a person was a short, medium, or long survivor in terms of ALS. So we have, for short survivors, we actually call an ALS patient a short survivor when the time between the disease onset and the death is shorter than 25 months. Medium would be between 25 and 50 months, and long would be longer than 50 months of survival after symptom onset. So this algorithm worked quite well. And now we put on top of this the aggregation levels of the random walker. So let's say some high level abstract network science feature, which would also be put in the machine learning algorithm. And what we found actually was that it actually helped to predict the survival class of individual ALS patients much better than without it, and increased the accuracy from 79% to 83% once we included the random walker. And maybe you're like, okay, survival is a measure, but how helpful is that if the patient knows when he or she will actually probably then die? There's something more interesting in ALS, and that's upper motor neuron score, which is based on the neurological examination here, where the doctor would just take a hammer, right, and test different things, and the patient would get a score. And we actually looked if we can predict those scores with our model. And yes, we found a nice relation that actually a higher score, so these are the upper motor neuron score, a higher score is bad, so it's worse, you can do less, patient is then less mobile. And we could predict with the aggregation levels at time point 1, whether a person had at the second time point, so about 6 months to 1 year later, what was his or her upper motor neuron score. And with that earlier, we will skip this a bit. And now you think, okay, this is all great, this is all structure. And structure is what we talked about so far in the brain, so the structural brain network, these connections, these white matter fiber tracts, and you can compare it with a road network. And once you have a road network, you don't know yet which way to take from A to B, because what you're interested in is the traffic flow as well, right? And that's the same for our brain. And we can compare this traffic flow network with the time series data we get of MEG, EEG, fMRI, whatever modality you favor. And then we call it the functional network. So for the brain, we have actually not only structural connections, but also functional ones. And that's where dynamics come in, and that's why we need the virtual brain. So, for example, let's not yet talk about the virtual brain, but let's talk about an epidemic spreading in the network. You can see it here. Red means infected, green means healthy. And this is a model where you can already see somebody can get infected in the network, but also recover again. We call it an SIS model, susceptible to the virus, infected by the virus, but also you can get susceptible again. What you can see here is the worst case scenario. The virus does not die out. It is caught now in what we call physically as the metastable state. So you would have a certain prevalence of the virus in the population. And since you can get reinfected, this just stays. Yeah, I will not comment how that relates to the present state of the world, but this is worst case scenario, it will never die out. If we think of this network science area of epidemic modeling, and I really liked it already here in 2017, I thought, wow, that also looks like activity spreading in the brain. And in the brain, it's good that it never dies out, right? We have a continuous level of activity spreading and different regions and giving activity and activating other regions. So I just went ahead and did it, put on the structural network an epidemic network model, SIS, and then looked at the different directions that actually the information, in this case, not the virus, but the information flows in the brain from back to front and front to back. And I found these two different directions of information flow through the brain just by looking at the simple SIS model that were actually happening on different time scales. Front to back was happening on a different time scale than back to front. So I just wanted to show this example a bit to tell you, like, there are so many different areas of network science, and some, like, for example, right now, epidemics is evolving very fast, and we can learn so much about it and also take there the newest developments and apply it to our brain network. All right, some other recent discoveries. Yes, I will show you a bit. For example, what I found when I was just looking for recent ones, Meier et al., they actually studied one female patient and scanned her for 30 days in a row and looked and found that the communities of the functional brain network of that lady changed over time from day to day. And these communities changed according to her hormone levels and changed right around the ovulation quite drastically. And also the default mode network, which is a very important one. So I found that quite funny. So you can think of all these different areas of network neuroscience where you can apply graph theory, and where with a simple abstraction level, you seem to understand already, without knowing the details, what's happening in the network. And here my former mentor, Martijn van den Heuvel, published a review, which I thought was quite interesting, summarizing how, hypothesizing how any disease spreads through the brain. So this hypothesis is that any disease in the brain would always start in one certain module and just be happening in that module in an early stage. But then at a later stage, once it got infected some of the hub nodes, which are well connected in the network, having a high degree, it then makes it possible for the disease to spread from one module to another module. So also damaging other modules. Within those other modules, you then have also failures. Then you have nodes that try to take over for those failed nodes, but they would also get easily overnoded. And what you have is a cascading failure of destruction in the brain network, leading to a very severe disease. So this is how you can think of many different diseases, of brain diseases, in terms of network science. So let's say an easy abstraction level to understand different kinds of diseases all at once. Some new trends in network neuroscience are actually once the temporal networks. So we no longer take the whole time series and just say, okay, that's one link these two nodes have over the whole time. But actually we take only those time windows and make for every time window a small network. And we then look how over time, even over the matter of minutes or seconds, our brain network can actually reorganize. And another thing is multi-layer networks. That's going on for a couple of years now, that you not only look at the structural or the functional one, but you have multiple layers of that network. And for the functional one, there's also multi-layer network discoveries where you have one layer for each frequency band, for example, in MEG, or you have an MEG layer and you have an fMRI layer. So you can just bring together all kinds of different networks to see the whole picture here. All right, and with that, I want to tell you about the virtual brain and brain networks, because of course, the virtual brain is based and its input is the structural network. So there's a lot of network science in the virtual brain. So here I just depicted it very in a very basic manner. In the virtual brain, we have those structural network here in blue, two regions being connected by a link. And then what we do with the virtual brain, we put on top of it the dynamics. So the dynamics are here, for example, we put an excitatory and inhibitory population model on top of every brain region. And then we let its activity spread. And how we connect the dynamics of one brain region with another is through what we call the global coupling. And sometimes this global coupling, this communication between the two regions also has a certain delay, because there is often a certain, let's say, street to cross between those two brain regions. All right, so the basis of the virtual brain is a network. And here is the most recent study which combines the virtual brain with network science. What was done here was just for 50 healthy people, the virtual brain was optimized, and it was fitted such that every person has a virtual brain. And then here one can see, we were looking now, focusing on this plot, that the average degree of the structural network in the virtual brain, so every person has a certain structural network, and we can calculate the degree of every region. And then we can take the average of all those regional degrees, giving us an average degree of a certain network. So for each person, the average degree correlated very highly with the optimal global coupling in between any two regions of that particular person. So what does that mean? That's actually quite easy to understand. If you have a very low average degree, meaning your connectivity in general is very low, you probably need quite a high global coupling value to compensate for that and still let those different dynamical models interact with each other to get meaningful activity over the whole network. If you have already a very high degree in your brain network, then the global coupling, which is a value being multiplied with every connection, right? Then you only need a very small one, such that we can level all those different individuals to make their structural networks quite similar, and then put on top of it these individual dynamics. All right, so that was actually found for these different models. And other parameters next to the average degree were also tested here, but none of them was found significantly correlated with the optimal global coupling. So there's still some work to do. All right, now I suggest that you don't panic, right? And we will dive into MATLAB. What we will do with MATLAB, as I said, you can also do. So degree is structural links and coupling is functional links. Yes, you can think of it exactly like that. Yeah. Good question. So what we will do with MATLAB here, you can do with any other language as well, right? I just prefer MATLAB because there's a brain connectivity toolbox out there, which is an open source toolbox where you can analyze brain connectivity, which is very easy to use. Yes, you can. I mean, you would expect it, but nobody checked it yet if there's a positive correlation if you take here it the other way around. So that's for you to check. All right, what we do with MATLAB is compare the actual brains of ALS patients and controls. This is not patient data or control data. This is LTIP data, but still we can do all the fun stuff as if it would be real data. And we'll do some network-based statistics on top of it. All right, so please open MATLAB and open a script, just an empty one if you like, to really do it yourself. And now I will dive into and slowly go through it. And actually what I prepared is a whole exercise sheet with solutions here. So a small kind of workshop. So if you feel like, okay, I really want to do this by myself and I want to take more time, this lecture will be soon on YouTube, right? Then you can there always pause and also try it out yourself. What I will do now is go through it and just invite you to go through it with me. You have already everything. If you've downloaded the folder from the link that Petra sent in the email, then you have everything ready to just execute the commands. But to really understand the commands, of course, it would be great if you just do the commands yourself. So always pause and try out to write it yourself and then look at the solution. For now, I will go slowly explaining the solutions, and I hope that you can already then just follow along a bit and maybe do what I'm doing at the same time. So we have the connectomes of 60 ALS patients and 120 age-gender matched controls. These are based on their first MRI scan of each individual, and they represent the structural network. Okay, yeah, it's not USB stick data, but it's from the link. All right, so in MATLAB, it's very important that where you downloaded this folder, Connectomics Practical, that you unzip it, of course, then you save it somewhere, and then you navigate there. Or what's important then, if you don't want to navigate all the way, you add the path, and this gen path is just adding all subfolders also to your path, making it available in MATLAB. And now, actually, so I am executing this. There are different shortcuts for that. You can also just copy paste it below into the command window. If you open this begin script student.m, there are already the solutions in there. So open an empty script if you want to do it yourself. All right, so we added the path such that we can use, for example, BCT, which is just a brain connectivity toolbox with all different functions for calculating all the different network properties that we've learned today. And here's a script with a begin script, and that's another script I wrote for you. Don't have to worry about it, can look at it if you like. And here's the test data. So what we now want to do is load this data, right? So how do we do that? We need to have the right path, or we can just drag and drop it also and execute this load command. This will load all the data here. Let's have a look. We have binary networks of ALS patients, which are just actually thresholded out of these weighted networks. Of these 60 ALS patients, each one having a matrix of 83 times 83, that's 83 regions connected with another 83 regions. And we have the same for HC. HC is healthy control, binary and weighted of the same 120 people. We also have region descriptions, and we have some coordinates here giving us 3D coordinates for every region. So now let's look at what the exercise wants from us. We want to visualize the first ALS patient in this format. And for that, in MATLAB, I will explain the commands now slowly. We will start making a figure. In this figure, we want the first patient. So we have 83 regions, take them all. And then we have 60 patients. We want to have the first one. So we set a 1 here. And then we take it off the binary one. We will do everything with binary. And I invite you to just do the same with weighted as well later on. And we do image SC. That's a command that gives you these heat maps or beautiful matrices. And we also will add a color bar. Let's execute it. It's coming out on the other screen, of course, as always. And you can see the matrix here. And the color is just giving you, when it's yellow, there's a 1 here. And because it's a binary network, we only have yellow and blue. So we only have 0s and 1s. Great. So this is the brain network of 83 regions, a real one. Okay. Now we want to calculate. That's great. Hope you didn't see that one. The degree of the precentral gyrus in the right hemisphere for each person based on the binary matrices. And then we want to know what's the average degree for patients and what's the average degree for controls. So in ALS, the precentral gyrus is often where the disease starts. So we would expect that the patients have a lower degree here, lower number of connections than controls. But let's calculate it and figure it out. So we first need to calculate the degrees. And that's what I already explained. We can just look at the matrix and we can take the sum of, these are symmetric, so row or column, however you like it. And that will give us the degrees. And here is now a vector where, for example, 24 is a degree of that particular node. Then we want to know the degree now of a specific region. In our case, the precentral gyrus. So let's find out where the precentral gyrus is. How should we know that? We look into the region descriptions. Just double click and you will see it coming up here. There's a list of region labels, how we call also in TVB, right? And you just have to find here the precentral gyrus. And then maybe you're like, precentral, that's the one. No, this means LH, left hemispheric. So we have to go lower and find it for the right hemispheric one. All right, so where do we put it? We put it either in the regions or in the columns or rows, it doesn't matter, it's symmetric. But we want to have now the region 71. We want to have a look at the degrees, and that's for all patients. All right, so for every patient, we now know the degree of the precentral gyrus. It's a lot of 17s, but also some are higher. So what's the average? To calculate the average, we just take this that we just created, precentral degree ALS, and take the mean of it. Not so hard, right? And we get average degree of ALS patients, 16.31. Now we just have to do the same for the controls. And you can just do it by executing this or rewriting it yourself to learn it, right? And now we are interested, what's this value, the average degree AC? And that's 16.8. So we see indeed that the controls have a higher degree of the right hemispheric precentered gyrus than the patients. So the patients already at their first scan here, they're showing some degeneration. The connectivity of the motor cortex is weakened. Not good. But we found it out. All right. It has a real lag here. Okay, which patient has the highest, that's our next exercise, has the highest overall clustering coefficient based on the binary matrices? Okay, clustering coefficient is quite important for the brain. We have heard it's weakened in Alzheimer's disease, yeah? So maybe it's a measure for cognitive disability, who knows? Could be, so let's find it out, which patient it is that has still the highest overall clustering coefficient. So for that, we would need to write something that we calculate the clustering coefficient for every patient. And how do we do that? We would have to look in the BCT, the brain connectivity toolbox, and there are different functions for clustering coefficient. And that's actually B for binary and D for directed. So we have in our case binary undirected. If you are unsure what it is, you can always double click and read that it is for binary undirected connection matrix. So always read the small header of these functions to be sure that it's actually doing what you want it to do. All right, so let's write a very small tiny for loop where we will calculate the clustering coefficient of our binary undirected matrix of all the different patients individually. And once we have this clustering coefficient, we also take the mean to get the global clustering coefficient. Let's do it. And we have a vector now, CALS, that's giving us the overall clustering coefficient for every different patient. And now we want to find where's the maximum. So we do find command of look at this and find where it's really equal to the maximum. Patient 43 is the answer. All right, so patient 43 has the highest overall clustering still. Great for him or her. And now let's look further. How many modules has the connectome of the last patient and of the last control? And which one has a higher modularity, the last control or the last patient? So look, again, remembering what's modularity. Modularity was how densely connected are the different modules. And if modularity is high, this is actually meaning we have quite a lot more densely connected modules than expected by chance. So that's good. If we imagine, as we've seen, the disease attacking different modules, we want to have high modularity, making our network quite efficient. Okay, so let's see, last patient or last control. So how will we go about this? We have the data, we have the binary matrices, okay. We would have to figure out what's the right function for modularity somehow in the brain connectivity toolbox. And you again see a lot of them. So you would have to go through reading the different instructions in the beginning of these functions, figuring out which one is for you. We take the UND, that's the undirected one, and we calculate it for the last patient, this modularity. So you just put ALS binary of all the rows, all the columns of the last patient. So the patient is here in the third dimension. And we do the same for the controls. And we want to figure out what's the modularity of these two. So there is a CI value, which actually this first value gives you the number of modules. So this last patient has 4 modules, and also the last control has 4 modules. So you would expect there is no difference. But actually there is a tiny difference. And indeed, it's a difference in the Q values, which is this modularity value, not giving you how many modules, but also how well connected these are inside of them. And for that, we can see a difference here, that a slight difference, that actually the QALS is a bit higher, right? Giving our last ALS patients a higher modularity, so modules being more densely connected among each other than our last patient. So that was just a comparison between 2 individuals. All right, so here we do now, I will already execute it, then we start explaining what it is. We will do a network-based statistic now. This is our permutation tests now running, because we want to know now the difference between patients and controls, right? Advanced exercise, you can do all of the same with other metrics, and you can do the same with weighted ones. And here we are asking ourselves if the links that have a significantly lower value in patients and controls. So we go back and we remember this network-based statistics, and we want to now compare every link with every other link in patients and controls over the whole group. And we want to see which links are significantly different than the other ones. So we want to find this cluster of low p-values and check out if it's a really large cluster and higher than when we shuffle the group or not. So for that, it executed here a lot of permutations. We just have to find the right function here in the brain connectivity toolbox. I have already this nice function, network-based statistics, brain connectivity toolbox, including a t-test, 2-sided. So we have no preference for higher or lower. And it executed 100 permutations of shuffling patients and controls among each other, building always 2 new groups, doing again the t-test, and every time step comparing this largest connected component of low p-values. And then it's showing us that actually here in the end, our p-value is 0.02. So yes, we found a cluster of largest connected component. So some interesting pattern of low p-values, which are quite different in between patients and controls. If you got a different value here, that's totally normal. In the solution, it's even called 0. I have run it today multiple times. It was 0.04 and so on, but always significant. So if it's below 0.05, you're fine here, but it's a random permutation, which can give you slightly different results each time you run it. So it's also great to do more than 100, right? Normally one does like 1,000 permutations here, but we don't have time for that. Okay, so there is this interesting cluster. So now in the last 5 minutes, we really just wanna have a look and see how that cluster looks like. All right. So before we do that, we ask ourselves still with network science a bit, are there differences found with regard to degree, clustering, or modularity that are significantly different between patients and controls? You don't only want to find the difference between one patient and one control, but now it's really over all of the individuals. We will calculate and do a small for loop over all patients and all controls and calculate the modularity. And then we do a t-test. So that's all the code you need to get, hopefully, once you have your own data between patients and controls, a publishable, nice result here, maybe significantly different. And you can start from there and say, hey, I found a significant difference between patients and controls in terms of their modules. But no, this p-value is too high. We found no significant difference here between ALS patients and controls. And the same we will do for clustering coefficient. No too high p-value, unfortunately. Then we will calculate the average degree. For that, we just take the average of the degrees. Squeeze is just getting rid of one extra dimension, so to make it easier for us. And let's see. No. Average degree, also not so different between patients and controls. And then if we look just at the precentral gyrus, we are close, but still no significant difference. So really all we have here is this connected component of interesting low p-values from our network-based statistic. So we want to look at it, we want to see it, and this is in the end now the nicest thing, I think. Let's have a look at the actual brain network and visualize it. We want to visualize this largest impaired connected component on the template brain using BrainNet Viewer. You can just download it, but it's also already in your folder, so you should be able to execute it. How do we do it? We need the connected component, which we saved under ADJ here. And we want to make it a full matrix. And we want to execute this nice little function that I wrote for you, plot BrainNet Viewer, that will generate the files that we need for the BrainNet Viewer. Then once you execute this, something like this should come up, the BrainNet Viewer. And all you now have to do is load this file that we just made and a surface. So there are different surface templates. You can choose different ones. I like the smoothed one, but whatever you like, take it. It's in the folder BrainNet Viewer. Then we need a file for the nodes, and we actually just generated, maybe you didn't even notice, a file a.node. We open this one for the nodes. We open this one for the edges, and okay. Then we get different options. You can play around with it, but we have no time for that. So let's just click apply. And here we go. We have now, from different views, the largest connected component that's different between ALS patient and controls. So actually the same result as in that previous paper. And we've just generated it ourselves. And you can click on play to get a rotation. Oh, that's so beautiful, right? Okay, you can play with that. Yeah, he doesn't like when I close it, sure. And the last thing that we want maybe is just for a nicer visualization, we wanted once look at one of these nice modules. So the module 1 of the last patient, we had calculated that earlier. Let's just plot that as well. So the module of the last patient, ta-da, BrainNet Viewer opens. We generated these files again. We again click on load file. We just load a nice surface. We just load the node file again. Same thing as before. We just generated new node and edge files that the BrainNet Viewer needs. Okay. Options, there are so many different options you can play around with. And again, this is the first module of the patient. Different views you can find here. So you can see quite a strong module placed together in the brain. And it turns, ta-da! Okay, with that, what can I open a mapping file? Yeah, good question. There are so many options in this BrainNet Viewer. Let's try it out. Oh, I closed it again, great. Okay, so let's say you can play around with it and find out different options that BrainNet Viewer is giving you, and there are so many, so you will recognize this visualization of BrainNet Viewer in quite a lot of publications in network neuroscience because many people are using it. And I actually don't know, would have to look up with the mapping file, but easy to find out for you. I just want to finish with all of this. I'm finished with the lecture, so I'm now here for all of your questions, and we can find out the answers together. Let me put you here. All right. Thanks to everyone who already wants to leave us, and for the others, I'm still here for questions. Also, I think we will stop the recording soon, such that you can come on camera and also discuss if you like in person.